We are now ready to actually talk about Isaac Newton's law of universal gravitation. You'll remember in chapter 4 when we talked about Isaac Newton's laws, we mentioned that Isaac Newton is very well known for his law of gravitation. So now we're actually able to talk about what that law is. First of all, some background. Um, Force of gravity is being exerted on objects. You're just walking around, you jump in the air, you feel the force of gravity pull you down. Well, what is the origin of that force? Isaac Newton realized that it must be the Earth itself. There had been a lot of theories in the past about something as simple as our natural state is at the surface of the Earth, and every object wants to go back to its natural state, so if it moves out, it tries to go back. That was an ancient Greek philosophy. Newton realized it was more than that. There is actually a force, a pull, that's pulling you downwards. Isaac Newton further realized that it's the same force that keeps the moon in its orbit around the Earth, that all the planets are in orbit around the sun, and so on. And so he started to work on finding an equation for this. So a couple of points about this gravitational force. It follows Newton's third law, meaning the Earth is pulling on us, but we are also pulling up on the Earth at the same time. Or on a larger scale, the Earth is pulling the moon downward, but at the same time, the moon is pulling the Earth upward. Every action, there's an equal and opposite reaction. Every force, there's an equal and opposite force. So the force on the moon is going to equal the force on the Earth. Now, that also needs to be combined with Newton's second law, which is that F equals ma, that the force is proportional to the mass and the acceleration. Or more appropriately, the mass and acceleration are inversely proportional to each other. So even though the Earth and the moon are experiencing the same force towards each other, the smaller mass, the moon, is going to accelerate more, while the larger mass, the Earth, is going to accelerate less. That's why the moon orbits the Earth and not the Earth orbiting the moon. If you were to look at very, very precise measurements, you would see that the Earth does move just a little bit. But the moon is the one that definitely does more of the motion. It's the moon that goes around the Earth in a very large orbit. Excuse me, there we go. While the Earth might be moving around very, very little bit because of the moon. But it's very, very minuscule, and it's hardly anything because the Earth is so much more massive than the moon. If the Earth and the moon were the same mass, what we would see is that the Earth and the moon would be orbiting each other. So this tells us that the gravitational force has to be proportional to both of the masses. So by observing planetary orbits, Isaac Newton was able to derive an equation. He determined that the gravitational force must decrease as the inverse of the squares, meaning force of gravity is inversely proportional to the distance squared. And so came up with the final form of the law of universal gravitation, which we still use today. And that is that the force of gravity is equal to the universal constant g, universal gravitational constant g, times the product of the two masses divided by the distance between the two masses squared. The universal gravitational constant has a value of 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. How do we know this constant? Well, Isaac Newton was able to figure it out pretty closely, but there was an experiment slightly later that was able to measure it more precisely. This is called the Cavendish experiment, where you just have a rod. You have a rod with masses on both ends, and it's connected to a mirror. So that if this rod turns, then the mirror turns as well. Then you shine a laser, which shines on the mirror and then hits a spot on the wall. Then you bring another mass, A, close to B. B is going to move ever so slightly because masses A and B are not very large, and so the force of gravity is going to be quite small between those two. And yet it's enough to cause object B to move just so slightly. And because it moves so slightly, it's going to cause this mirror to turn, and the laser is then going to read at a slightly different point, and so you can tell exactly how much it turned. And so it's pretty cool. You can actually measure the universal gravitational constant using the Cavendish experiment. All right, so now we have two equations for the force of gravity. First, we have that F equals mg, and now we also have that the force of gravity equals g times the product of the two masses divided by r squared. Okay, remember in the last couple slides that said m1 and m2? I'm going to write it as capital M and little m for the following reason. Remember that when we calculated it as force of gravity equals mg, which mass did we use there? Well, that was the mass of the object being pulled down by gravity. If we were talking about the weight of a box, it was the mass of the box. If we were talking about our weight, it's our mass. So little m is then going to be the mass that's being pulled by gravity. And so big M has to be the other object involved, which in the case of the box or our weights, that would be the mass of the Earth. So we're going to use capital M being the mass of the object that is pulling, that is exerting the gravity, and little m would be the mass of the object being pulled. But both of these are equal to the force of gravity, so we can set them equal to each other. Well, if you divide out the mass that is being pulled, that gives us an equation for the acceleration of gravity. That is the universal gravitational constant times the mass of the Earth divided by the radius of the Earth squared. Okay, but what is the mass of the Earth? Well, we know g, we know the universal gravitational constant, and we know the radius of the Earth. So we can actually calculate the mass of the Earth. If we solve for the mass of the Earth, that would be gr squared over gravitational constant. Plug all those numbers in, you get that the mass of the Earth is 5.98 times 10 to the 24th kilograms. All right, but now I have to put a qualifying statement on this. We have always said that little g, gravitational acceleration, this g right here, is 9.8. And that's what I use in the equation. Is it always exactly equal to 9.8? Well, no, because little g also depends on the radius. This little g is equal to 9.8, assuming that the radius of the Earth is 6,380 kilometers, which is the number we used here. But the surface of the Earth isn't smooth. It's not a constant elevation, so therefore the radius of the Earth also changes. So you can see that, for example, San Francisco, where the elevation is 0, your g is equal to 9.8. But at New York, where the elevation is equal to 0, g is equal to 9.803. Why? Well, the Earth is not a perfect sphere. The Earth's radius is actually larger near the equator and smaller closer to the poles. Since New York is closer to the pole than San Francisco is, then its radius is going to be smaller, giving you a larger value of g. Sydney, Australia is closer to the equator, so it has a smaller value of g. The equator itself has the largest radius of all sea level points, and so at sea level at the equator, g is actually equal to 9.78. If you go to places like Denver that have an elevation of 1,650 meters, you have to include that elevation into your calculation for g. And so that so your g actually changes because of the increased elevation. Let's try that out. City of La Paz, Bolivia, has the highest elevation of any city in the world. It has an elevation of 11,975 feet, or 3,650 meters. So what's the value of g in La Paz? Well, we're going to assume the radius of the Earth is 6,380 kilometers. So we're going to use our constant, or our equation that gravitational acceleration is the gravitational constant times mass of the Earth divided by r squared. But r is going to be the radius of the Earth plus the altitude. So if we plug all those numbers in, you have your gravitational constant, mass of the Earth, and the radius would be 6,380 kilometers, or 6.38 times 10 to the 6th meters, plus the altitude of 3,650 meters, gives you a value of 9.788 meters per second squared at La Paz. And again, that is assuming that the radius of the Earth is constant, which we learned in the last slide that it's not.